start soon. Just waiting a few minutes for people to join in. Okay, then I think I can start with a general introduction. So welcome everyone again. Thank you for joining today's FHI AIMS webinar. And today's topic is on advanced electronic structure methods for battery design and vibrational spectroscopy. And we have two great talks scheduled for today. And we'll start with the first talk, which is by Mariana Rossi. Mariana Rossi will talk about vibrational spectroscopy for periodic solids and liquids in FHI AIMS. And she obtained both her bachelor's and master of science at the University of Sao Paulo in Brazil, and has been for long in her PhD at the Fritz Haber Institute here in Berlin, and then also was a group leader at the Fritz Haber Institute, and is now an independent Lise Meitner research group leader in the Sabia group. And just in case people are wondering what the bird is supposed to represent, so I found out by researching that it's also an indigenous bird to Brazil, which is called sabia. Maybe not the correct Portuguese pronunciation, as Mariana can tell you, but yeah, it's supposed to represent the bird as well, which I think is quite nice. That will be the first talk, and we have a second talk then scheduled afterwards, which will be given by Alexander Chachenko on unlocking ionic puzzles in solid electrolytes with FHI AIMS. And Alexander is currently a professor for theoretical condensed matter physics at the University of Luxembourg, and I think also the head of the theoretical chemical physics group. He also did a longer tenure at the Fritz Haber Institute, where he led a group from 2011 to 2016 at the Fritz Haber Institute here in Berlin, and then transitioned to the University of Luxembourg. So we are very happy to have both of you here, and I hope you will all learn something about both of these topics. The webinar itself does not only have one day, so we have these talks for today, but then we also have tomorrow tutorial sessions. And this is meant to be open for everyone. So even if you don't directly, for example, want to do the online tutorials, you can still use this time to ask questions, start discussions on FHI AIMS related work, or general questions to condense computational physics and so on, if you have any. So we have two slots, 9 a.m. CET in the morning Berlin time, as well as one later on at 4 p.m. CET. So feel free to join either of them. The link will be the same as you're currently using for the webinar. And if you signed up beforehand to do the hands-on sessions, you should have already gotten instructions this morning on how to log in and essentially just the registration details for how to run the tutorial. I will walk you through all those things also during the hands-on session. So for both, we have also short introduction videos to FHI AIMS on our YouTube channel, as well as a Slack channel in case you have any questions. What we'll talk about during the tutorial is directly related to the two talks we hear today. So one is on simulating vibrational spectroscopy with FHI AIMS, and the other is on calculating some diffusion barriers with FHI AIMS and also the AIMS chain package. So this is what you'll hopefully learn today. And this is just a short introduction. And then we can start with the first talk. And the first talk will be given by Mariana Rossi. So Mariana, please feel free to go ahead and share your screen.
Yes, thank you. So hopefully this works. You see my full screen now with my slide, yes?
Yes, perfect. Thank you.
And do you see my mouse when I did?
We see your mouse, yes.
Thank you. Yes, perfect. Then I will start. In this first part of the webinar is supposed to be 30 minutes, and Konstantin, I have some time here, but if you can just give me a little bit of a cue by the end, that would be great. So as Konstantin already introduced, I'll be talking today about vibrational spectroscopy in FHI AIMS. Actually, vibrational spectroscopy is what I'll focus on the second part of my talk. The first part will be basically an introduction to what FHI AIMS is, what is the code, what is the underlying framework with which we can perform this type of vibrational spectroscopy simulations. And that part will have a little bit of an overlap with previous webinars just to set the stage. And then we'll move into the vibrational spectroscopy piece that is a little bit more focused on what I'll show today. And then on the second talk is Alex talking a bit more about a scientific case of the solid electrolytes. So yes, as Konstantin mentioned, I'm in Hamburg, Germany, and my name is Mariana Rossi. In case you do not know me and we have never met before, this is a photo of myself with my group at the end, at fall, beginning of fall last year. And we're an independent research group hosted at the Max Planck Institute for the Structure and Dynamics of Matter, as I mentioned, in Hamburg. And the group is called Simulations from Ab Initio Approaches, but it has this nice acronym that Konstantin mentioned, which is SABIA, which is a bird from the country I am from, where I grew up in and where I studied most of my life until I moved to do my PhD abroad. So that's us there. And in this group, myself and many of the members, we contribute to and co-develop the FHI AIMS code. And I am also one of the coordinators of the code. So moving on to talking about FHI AIMS itself. So FHI AIMS is a code that started around 20 years ago in the Fritz Haber Institute in Berlin. And the code was developed with this vision that is written here, that we wanted an electronic structure code that could really treat realistic and complex molecules and materials and give a prediction of their properties from the point of view of electronic structure without sacrificing accuracy even when you go to large sizes, right? And so the framework that we have today is something that achieves an all-electron implementation of electronic structure problem in terms of the Kohn-Sham DFT mostly, but I'll talk more about it later. It can treat both non-periodic and periodic systems on equal footing, so you can really go through both types of simulations in the exact same code. It achieves a really great scalability up to large system sizes. We can do many thousands of atoms. You will see actual examples in my talk about that. And we don't have to sacrifice accuracy or precision. And the current version of the code really achieves this scalability that I can do, simulations on my laptop or, you know, on massively parallel high performance computing architectures. And it works in both cases, of course, depending on the size of your problem that you want to solve, but it really scales very well and is also cheap enough to do in your computer, in your own laptop if you need. And of course, I mean, one of the nice things is also that even though, let's say, I would say at least that the workhorse of the code is really ground state density functional theory, it also has a huge support on explicitly correlated methods and very advanced implementations of random phase approximation, GW, and couple cluster via some interfaces, for example, to CC4S and other explicitly correlated methodologies as well. So all of these all these bullet points that I have read through and mentioned now are really possible because in the code there is this critical choice that was made that the basis set are numeric atom-centered basis functions. Yeah. And this is really critical to achieve this efficient all-electron implementation, to achieve scalability and many other properties that I'll go a little bit more inside into soon. The last thing I want to mention here on this slide is that nowadays the stewardship of the code is basically hosted in this non-profit organization called Molecular Simulations from First Principles. The purpose of the organization is to support basic science and to support the code. The advisory board of the organization is made by myself, Matthias Schäffler, and Volker Blum. Volker Blum is also the person that did the slide originally that I am showing you today. And he's also the person that wrote the first line of this code almost 20 years ago. He continues to be doing a lot for the implementations and the coordination of the code, of course. And of course, it's not only us. Actually, the code is really, the development of the code is based on a large and very active community. So it's a community-based code that gets a lot of scientists contributing to this. Yes, so going a little bit more into the critical choice of the numeric atom-centered functions, this is how it looks like, and you know, this is something special of FHI Ames. Let's say that this formula you see here on the other screen, this formula that you see here on the left, it's usual. Many of you have seen this before. So psi k of r here represents, for example, a single particle Kohn-Sham orbital. And you do a linear expansion of this Kohn-Sham orbital into some linear combination, right, of atomic orbitals. In this case, it's basis functions here, phi I of r. And these are the basis functions that are numeric atom-centered orbitals that we use in the code. So they're atom-centered, as the name says. So each atom in the system will have its own set of basis functions. The basis functions are given here by the expression that you see in red. So it has an angular component, which is just a common spherical harmonic, YLM. And then the radial part is really the crucial part, let's say, that has a lot of flexibility. It's numerically tabulated on a dense logarithmic grid in the code, and it's splined very smoothly and so on. And it can provide the necessary flexibility to describe these fast oscillations that you have close to nuclei in an all-electron framework. At the same time, because they capture this so well, you end up with a small amount of basis set that can very accurately give you, can quickly converge the total energies and so on. So you don't need large basis sets. So the code is also efficient because of that. And also because these functions, they decay to zero here after some distance that they go away from the nuclei they are related to. We can also apply a cutoff potential that really makes them strictly zero after that cutoff, and that makes the whole framework strictly localizable. So for most integrations that we do in real space in the code, actually we can achieve this order n scaling because we are localized, because the basis sets can be localized, and so the code scales basically for all operations except the eigenvalue solver as order n. The eigenvalue solver is also not the bottleneck of most calculations unless you go to very, very large system sizes. So when you look at scalings in the code, you typically see order n for up to very large system sizes. And the nice thing is that these basis sets, they are shipped with the code. They have been optimized for all elements from, as you see in the slide, from 1 to 102 atomic number, and they deliver really accurate and precise results for a cost that is not really large. And this accuracy and precision that I'm talking about, and also the scalability, they are not just words. Of course, they have been benchmarked by ourselves and also by a larger team of colleagues in the literature. And these are some of the papers you can look up. So this is one paper from 2016, which is the famous Delta test that was comparing many different electronic structure codes in order to yield the equations of states of I think 70 elemental solids. And they conclude that all electron implementations are really the most accurate and precise, and FHI Ames came as one of the most precise codes there. Then there was this other study here, which was looking at molecules and total energies of molecules, and they look at several different types of basis sets that code uses, like Gaussian basis sets or STOs or numeric atom-centered orbitals, and they also actually see that numeric atom-centered orbitals deliver better accuracy on total energies of these hundreds of molecules that they looked at. This is another benchmark which looks at electronic band structure and spin orbit coupling correction, so how precise that can be in the code, arriving to a good result in the end. And finally, I would like to highlight also this contribution from 2023. It's a roadmap that looks at the, several different electronic structure codes and how they fit into this exascale computing era, and they represent and quote a few scaling benchmarks and so on of FHI Ames if you're curious how we have benchmarked that. So of course, everything is a continuous work and we continue to improve all the time. So even after all of these papers, basically, we continue working. So this is an even more recent paper that I'll quote in a moment. So from the beginning of 2023 to the end of 2023 up to the middle maybe of 2024, we did a lot of improvements on the GGA functionals, as I show here, and also on the hybrid functionals implementations in the code. So what you see here are two systems that I particularly was interested in and I benchmarked. This is an ice structure with many, many molecules, 512 molecules, and this is a van der Waals heterostructure. And this is just the time per SCF iteration that we had in the 2022 version of the code in yellow and the 2023 version of the code in orange. And these were improvements that we did on the handling of the Hartree terms, so the electrostatic terms in the code. And you can see that for some systems we can get a larger speed up than others, but it's very nice. It's becoming faster every time. This was just a rewrite of how we write the routine, so it's more computer science than it's not a new algorithm, but rather restructuring the code. Much more dramatic than what happened to the GGA functionals was what happened to the hybrid functionals. So there we also looked at the implementation, the periodic implementation of hybrid functionals, and we already had an implementation in the code since 2015, basically. And this is for gallium arsenide supercells and the HSCO6 functional, which is a range separated hybrid. This is how the dashed lines is how the code was scaling in the previous version. From green to purple, you increase the number of atoms in the system. And these lines here below, which are the full lines, is how the code is scaling nowadays. This is with number of cores, you see. And what you see is that the new implementation, which has more layers of parallelization, it parallelizes over different elements in the code, basically. So we changed all of the layout, basically, of the implementation. It achieves really almost ideal strong scaling, and the prefactor is much reduced. So we have a time to solution reduced by basically 2 orders of magnitude. And this is also reflected in the order n scaling here. So now this is how it scales with number of atoms. The original implementation was also order n scaling in that respect, but with a much, much larger prefactor than we have now, right? So that this current status of the implementation really allows us to do very large simulations with hybrid functionals, or do very, very fast and very, very efficiently simulations for smaller system sizes. This, and also these improvements in the electrostatic potential and so on, they are all summarized in this publication, the JCP from last year. The two first authors here, Sebastian and Florian Merz, are the ones that are responsible for all the incredible wonders that were really achieved. They coded most of the things, and the rest of the authors, we were talking a lot and we helped, but I feel that they really deserve a lot of credit for this. And so what we show there is that now we can achieve simulations. You see, this is a plot of the paper. If you're interested, you can look at more details there. That we show calculations with hybrid functionals for systems containing up to 30,000 atoms in the time per SCF step. That really is okay for this type of system, right? So it's a very, very fast, very, very efficient, and it's amazing what we can do now with that. So that's not all. Like, we also have a very, very advanced implementations of dispersion corrections in the code. And this is something that the next speaker, Aleks Tkachenko, is the person that drove the first implementations for sure. So this is the 2009 paper from Aleks and Matthias Scheffler, where they proposed the pairwise van der Waals correction that was first implemented in FHI AIMS. And of course, it's still available there. It's a very successful correction. After that, there was also the many-body dispersion correction, which is also available in the code. And even more recently, this many-body dispersion NL that extends a bit this many-body dispersion framework for systems that are highly polarizable and so on, so it can treat more effectively metals and for example, two-dimensional materials like TMDCs and so on with this approach. It's also available in the code and with a very nice implementation through this libnbg that Aleks also supports in his group. And then we also have now some other let's say van der Waals corrections from other families of van der Waals corrections. So the XDM by Erin Johnson and Axel Becky. This is the exchange dipole moment corrected hybrid type of van der Waals correction. It has forces and everything in the code, so it's a very nice implementation that you can also use. And more recently, even Grimme D3 correction has been put into the code. So the nice thing is that you can look at all these different types of corrections within the same framework and see how they fare for your system. Okay, so now that we have all of that and all of these tools, the question is really, can we simulate vibrational spectroscopy with FHI AIMS? And this is the second part of my talk. And I would not be giving this webinar if the answer was no. So of course it's yes, that we can simulate that. But I'll try to tell you a little bit how we can get the ingredients to do these simulations and which types of functionalities of the codes you have to use in order to do that. And then more hands-on, you'll see in the tutorials how to actually do it. So if you want to actually hands-on do it, this will be in the tutorials. I'll show you here a bit what you need and how it's implemented and so on. So vibrational spectroscopy, maybe as many of you that are here today know, is a very important technique to be able to experimentally realize or simulate, because it gets the material to tell you something about its nuclear motion and the allowed vibrational transitions, which in turn can give you a lot of information about what is the structure of the material, what is the chemical composition of the material. It can probe what types of bonds you have in your systems. It can probe the potential energy surface and much more. And so, of course, there's a huge interest in simulating that, and also a huge interest in being able to simulate something that you can directly compare to an experimental signal, right? So there are many different types of vibrational spectroscopy techniques, including linear and non-linear ones, enhanced, plasmonically enhanced ones, resonant or non-resonant ones, and so on. So the zoo is very, very large. And for each one, you need a different kind of ingredient, let's say, in order to be able to simulate that spectrum. There's a lot of theory that goes behind getting these expressions that you need to calculate in order to simulate the spectroscopy that you want to compare to. But the most widely used, or the ones that are most common to see, is infrared absorption and Raman scattering, right? So these are the most common ones, and they are types of linear spectroscopy. Okay, so I show here in the table, like this is work after you figure out what type of spectroscopy that you're doing, and then you figure out what is the cross section, either the cross section of absorption. So what is the probability of absorption of your system? This is in IR, or the cross section for scattering. That's what you need in Raman. And I show you here two ways of calculating each one of these spectroscopy. On the first row here is the double harmonic approximation that is called. So that these are the expressions that you see here on the top. So the IR intensity for each normal mode, harmonic normal mode of vibration, is given by the how much the dipole will change with respect to displacements along this normal mode that I call here QI. And for the Raman case, you see that it's then how much the polarizability tensor will change along the displacement of the same normal mode. I'm writing all these expressions here in simplified terms, as I put here on the bottom, because of course this polarizability is a tensor. So, you know, like you need to see which components of the tensor you need to look at. The same thing here for the dipole. That really depends on the experimental signal you want to compare to, how you combine the different components. But the ingredients are those. And this is a harmonic approximation, or even double harmonic, how it's usually called. But the anharmonic case is also possible to be calculated. The expressions are here on the bottom. Within linear response, again, these are given by Fourier transform of some time correlation functions here, the dipole time correlation function or the polarizability time correlation function. So I put here in orange the ingredients that you need, right? So if you want to go about calculating this type of spectroscopy signals now in your system, what do you need? You need some way to calculate the dipole for either periodic or non-periodic systems. You need to be able to calculate normal modes, and the normal modes that are interesting for this kind of spectroscopy are the ones close to the gamma point of your crystal, if you have a crystal, because normally in these experiments the wavelength that they shoot in is such that you're only sensitive really to modes close to gamma in most of these cases. So that's the ones you want here. And here, if you want the fully enharmonic, so then you want also the polarizability in the case of Raman, these you obviously need. And if you want the enharmonic case, this time dependence here, both of the dipole and of the polarizability, they come from the time dependence of the evolution of the nuclear coordinates. So what you actually need is how to evolve your nuclear coordinates in time, and then you can calculate this type of correlation functions. So these are the ingredients, and the question is, how can you get these ingredients from FHI-aims? So you might have seen also in past webinars, I think the one from Matthias Scheffler, that there is this new code review roadmap coming out. It's currently at the draft stage, but I think now Basti and Constantine, people here can correct me, but I think that we're planning to send it out really in the next 2 weeks or so, even to archive. So if you need it sooner, you can email us, we can send you drafts, but otherwise it should be soon, at least in archive. And in this review, you will see several contributions that I walk through here that explain to you exactly how to get each one of these ingredients that I just mentioned in order to calculate vibration spectroscopy. So the first one is, let's say you need phonons, right? You need this, if you want to calculate this in the harmonic approximation, you need phonons and vibrations for your systems. And this is covered here by this contribution, which has number 6.1, that was led by Christian and Matthias, and Tom Purcell as well. And I would like to say a couple of things about how to calculate this in FHI-aims. So for us in the code right now, we recommend you to do finite difference algorithms for phonons instead of density function perturbation theory, because the density function perturbation theory implementation in the code at the moment for nuclear displacements, right, the ones that could give you the dynamical matrix, the Hessian, and so on, has limited support. I will come back to that in the later slide in my talk. While finite differences actually are not that much more costly for system sizes that are typically the ones that you need, and it will be accurate for any functional that you use and so on. So you always get the good answer, right? So that's what we recommend, to use this. And these finite difference algorithms can be done with FHI aims very simply, for example, by interfacing with FHI vibes, which bridges to phonopi. And this is a very tight connection to FHI aims. So it's built for FHI aims, and it's very easy to do phonon calculations with this code. You can also use phonopi itself directly with FHI aims if you wish to do so. It has an interface. You can do it also through ASE, which also has an interface to FHI aims as a calculator, as many of you might know, and this is also possible. The IPI code can also do that interfaces through the sockets or in-house scripts that you will see one example in the tutorial that can really get you the whole infrared and Raman intensities by an in-house script that connects everything. That we'll see in the tutorial tomorrow, right? On the other hand, if you want to do the enharmonic case, then you need to really get the nuclei to move. This you do through molecular dynamics. And the molecular dynamics in FHI aims is also covered by another contribution in this roadmap. This one here, 6.2. And there are several ways as well to perform molecular dynamics with FHI aims. There's a native implementation, which is quite robust, but has limited features in the sense that, for example, there is no barostats implemented, so you cannot do constant pressure simulations, and it's a bit limited in terms of which integrators you can use or which type of things you can do. So, but it's very robust. If what you need is represented there, then you can of course use that. FHI vibes bridges to ASE, so it actually uses the ASE molecular dynamics module to do also molecular dynamics with FHI aims, so you can also do that. ASE itself, of course. And IPI, which is my personal favorite because I also developed IPI, but that's another story. But in IPI, you can do, if you need to do very advanced types of molecular dynamics, including maybe nuclear quantum effects and so on, that's the code to go. It has very advanced techniques implemented in there, and it can give you lots of features there. And all of these work through socket interfaces, so it's quite efficient as well to do it with FHI aims. You don't lose any efficiency in this case.
5 minutes, roughly.
Yeah. But then that's not all. So you have, you need dipoles, also not only for clusters, but also for periodic systems. For clusters, it's quite straightforward to calculate. You just calculate the integral of the density times the spatial coordinate over all space. And this is, it's in the manual, you can really see that. But for periodic systems, it is more complicated because the dipole is related to the polarization, which is really defined as a geometric phase of the wave function through the modern theory of polarization. So you really need that to have boundary insensitive results for the dipoles of solids, or of really periodic solids. And this is something that has been implemented more recently in the code by Christian Carbonio. He did the implementation. And it's also summarized in this other contribution here in the roadmap. You can see in this case you need to take a bit of care because this quantity is multi-valued, so it's calculated like this with the Berry connection. This is the A here, and it comes in several branches. You need to branch match to be able to get dipole differences that you need for the dipole quite nicely. You see a bit of that, I think, in the tutorial tomorrow. And finally, the polarizabilities, which are then a response property of the electronic density. And this can be calculated by electric field perturbations on the electronic density in the framework of density functional perturbation theory for electric fields, right? And this is particularly useful, again, for periodic systems because you also need here a boundary insensitive formulation for this quantity. It's related to the polarization, of course. And in this within the framework of the FPT for electric fields is quite nice to calculate. And we have an implementation there since 2018 by Honghui Shen that has been recast and reorganized and made more robust and more compatible with the rest of the code by Connor Box more recently, and that's also in this contribution here of the roadmap. These are also in archive. This is a figure from that contribution where you can see for the density functional perturbation theory parts of the code, what is supported, what is not supported. Connor did a really great job summarizing that. And you will see that for electric field responses, basically most things are supported and it works quite well for all systems. But for atomic displacements, that's what I mentioned in the beginning, not so much. So it's limited support. Okay. And then I'll take the last 3 minutes basically to show if you get all of this data from FHI Ames, what you can do or what you can discover with that. So in this case here, I'm showing a publication from my group from 2019 where we looked at molecular crystals. And you see here we calculated Raman spectra for 2 polymorphs of paracetamol crystals. And this is the low frequency range. And you see that you can really differentiate these polymorphs by this low frequency range. You see here in the bottom, that's experiment. They see it's really different signal, and that is used actually to know which polymorph you have. And here, as you see, I calculated that harmonic approximation Raman or in the anharmonic approximation, and you can see that some peaks shift anharmonically, get closer to experiment, and it's really nice, and we get really good matches with the experiment. You can also do IR spectra for molecules, for example. This is something that I did also in 2019 for this 415 molecule. You see in green here is the infrared spectrum that was measured. In red, it's what you get from a harmonic approximation. It really doesn't match experiment at all. Even if you do anharmonic, but with classical nuclei in this case, it's the blue line, you don't get very good agreement. But if you include the quantum nature of the nuclei, which is something I'm not covering today, then you get really good agreement with the experiment because the hydrogens here really delocalize in this case. And this was basically, so this is 2019, this is the past. We were doing ad initio molecular dynamics. Nowadays, we machine learn everything. So of course, you can machine learn all these types of spectroscopy as well. And this is something we have been working on also since 2019 as well. So we show that we can learn polarizability tensors for crystals from FHI Ames, and then this again the Raman spectra for paracetamol. In blue is what would be the full ab initio calculation, and in black is our predicted spectrum from this learned polarizability. So that's very good. We showed we can also learn the infrared spectrum by learning the dipoles on the first hand. And then we could look at the temperature dependence, again, of the IR spectrum of the same molecule I showed in the slide before. More recently, we showed we can also learn directly the electronic density response to electric fields. We have 2 papers, a paper that also just came out in archive last week, that we show how to do the full electronic density response. And with that, of course, you can, again, reconstruct the Raman spectrum. For example, here is of naphthalene, and it's a very good match to what would be the full calculation. And even more recently, this is something that will probably be submitted tomorrow, is a model where we learn the dipoles for periodic systems, and here is just the infrared spectrum of water under applied electric fields that we are doing in the group. So I just want to mention that all of this has been powered with data from FHI Ames, all of these results that I showed you here. So even in the machine learning era, the accuracy, in fact, of FHI Ames has always brought me a lot of joy, because then the machine learning methods can really learn without problems. Also for these, cross-sections, so the polarizability, the dipole that you need to calculate this type of vibration spectroscopy. And that's it. So thank you very much, and please ask questions.
Thank you, Mariana, for your very nice talk and introduction. So this opens up the second part of the talk, which is the Q&A session, which will be roughly 15 minutes. You can ask questions in the Q&A functionality here in the webinar. So if you click in the toolbar, you will see a Q&A option where you can ask questions directly, and these are we already have 2 in the chat. You can also ask on YouTube. So we already see also a question on YouTube or on Kushare. So feel free to use all of the platforms and we'll try to answer as much as possible. The moderation will be done by my colleague, James Green. So he will take over the Q&A. And thank you again, Marina.
Thank you, Konstantin. And yeah, as well as the typing in the Q&A, if anybody wants to speak their question, then you can also raise your hand and I think we can unmute you so you can speak directly as well. But yeah, I'll start first with the ones that have been typed in the Q&A. So I have two by David Abbasi. So the first one is thanks, Mariana. From harmonic calculations, you get the normal modes. However, when you calculate the anharmonic spectrum, is there a way to assign what modes each peak corresponds to? Somewhere I've read one can use the piglet methods in IPI, but I'm not sure about the methodology. Do you have any experience with that?
Yes. So when you do the anharmonic calculation, it doesn't come directly out of the simulation what modes are what, right? There are several ways that you can post-process and analyze this kind of simulation. So if your system is not horribly anharmonic, normally if you project on the normal modes, then you can project your trajectories that you get on the normal modes of vibration, and then you can see which modes are ringing where, right? So then you get a spectrum for each projected normal mode, and then you can see what peaks are contributing to each mode. If it's more anharmonic, then the picture will become very blurry, right? Because many modes will mix and they will contribute everywhere, and what is it really any of that? Then you can do many different things. Some things that sometimes people do is to define a renormalized Hessian, so or dynamical matrix, something that is more consistent with the temperature dependent normal mode, something like that. So there's a lot of that in the literature, and then again do the same projection. So it's kind of a renormalized harmonic basis or something like this. And then you understand things like that as well. Or you really look at motion in Cartesian space. I mean, you have to do some post-processing. That's I think my main message. And then there's, I think, an unrelated question, I think, about Piglet in IPI. Yes, you can use Piglet. So Piglet is a thermostat that uses colored noises in path integral framework in order to accelerate the convergence of path integral calculations with the number of replicas of your system or beads that you use. It's not relevant in the context of vibrational spectroscopy because this type of thermostat really messes up all the correlations in your potential energy surface. And because here, for this type of spectroscopies, you need to calculate an autocorrelation function, and it needs to be faithful to the correlation structure that your Hamiltonian gives in your system, then you cannot use this type of thermostats to calculate any of that, in fact.
Okay, thank you. Hopefully that answered the question. And another question from David is, can you comment on how you learn the polarizabilities?
Yes. So, so let's say, so this paper here, if you look at that, so what we used is here it was a symmetry adapted Gaussian process regression model in which we took into account the symmetry of the polarizability tensor into the learning problem. So this is a Gaussian process regression, but the kernels that we use are different depending on the lambda order of the piece of the polarizability tensor that we want to predict. So there's the isotropic part that transforms like lambda equals 0, and the anisotropic part that is lambda equal 2 for the polarizability tensor. So we have different kernels that keep these symmetry transformations in the SO3 space, and then what we do there is that simply we get a lot of structures for which we could calculate the polarizabilities or the periodic polarizabilities with FHI aims, and we calculate the smooth overlap of atomic positions, so SOAP descriptors for all of that. That is what we use as inputs to build the kernels for the training set. And then we have the answer of the polarizability. We train the model by just doing the linear inversion of the GPR. And then we predict in a new structure by also representing it with slope descriptor.
Thank you, Mariana. So a question from the YouTube comments, so from Daniel Diesenbeck. Is it possible to perform thermodynamic calculations after performing the vibrational calculation? And do I need to ignore the translational and rotational modes, or does the program ignore them?
Can you read again the first part of the question?
So is it possible to perform thermodynamic calculations after performing the vibrational calculation?
I am not sure what is meant by thermodynamic calculations.
So maybe
in this context.
Free energy calculations. So
yes,
vibrational free energy.
Yeah. So yes. So this is something that I do believe, and I think James, you also know this. So the script that you will use tomorrow, it calculates the ZPE, right? But does it calculate the free energy too? I think not. No. So so out of the top of my head, I don't remember whether we have any utility script that actually calculates vibrational free energies from anything. So the main message I would have to you here is that yes, indeed, once you have the normal modes of vibrations and the normal frequencies and the harmonic approximation, this is all you need to calculate something like free energies, right, of the system. Whether that is shipped with the code or not, I don't know. And maybe tomorrow we can answer this question more. Personally, I have my own scripts, and in my group we have our own tool set of doing that. All we take as an input is the normal modes of vibration and normal frequencies. And then whether you ignore or not in solids the first 3 vibrational modes, or in molecules the first 6, right? Because vibrational end rotations. That depends on the script. It is not done automatically inside FHI AIMS.
Yeah, maybe I could just comment on this also. So the script that's used in the tutorial tomorrow, so the Python script doesn't compute these free energies, but we do have a Perl script in the code, which is referenced in the tutorial, but we don't actually use, which does calculate these, say, vibrational free energies. And it is our intention to put this into the Python script in the near future as well, and add additional.
Yes, and it could be that FHI Vibes does this also. I'm not so sure, but it could be. Yes.
Okay, so more from the Zoom questions. So Sandeep Kumar, what role does electron-phonon coupling play in the Raman spectra of superconducting or topologically interesting materials, and how can this be accurately modeled within the DFT framework and FHI AIMS?
Not my area of expertise. I will not. So electron-phonon coupling can be calculated in FHI AIMS. This is not the topic for today, but this is possible. So it's within the framework of DFPT. Electron-phonon coupling is well supported. There is actually also an entry of this roadmap that only talks about electron-phonon coupling. So if you were curious about the roadmap, it will also be there. So in that context, yes, it's possible to calculate electron-phonon coupling. What role it plays on the Raman spectrum of superconducting systems, not my expertise. I'm sorry, I cannot answer. I think it really depends on what superconducting system you're talking about and what type of superconductivity you have. But I don't know. And yes, I mean, but if what you're after is electron-phonon coupling matrix elements, yes, you can do. And maybe I would speak one more thing about something related, that FHI AIMS is really great to simulate 2D materials, because you don't have to pay anything to put a vacuum in your system, because it's all localized basis. And so if you're looking at this new type of 2D materials and so on, and quantum materials in that realm, it's really great to do calculations with FHI AIMS. You can do it very efficiently when it's doing that.
Thanks, Marianne. So the next question from Raji asks about the link for the FHIM's roadmap, and it's online, so maybe I can just quickly answer this by saying, yeah, Mariana said that it should hopefully be put on archive and complete in the next few weeks. We have pieces of it available at the moment, so one of my colleagues will type in the chat the links to the pieces that are available right now. And also, if you're interested in the full version at the moment, you can email us as well, and we'll send the email address that you can speak to as well. Okay, so next question from Aurélie Champagne. So they have two questions. So in addition to vibrational spectra, run an IR, is it also possible to compute NMR spectra and or absorption spectra? That's actually electronic absorption spectra.
Yes, NMR, yes, it's another incarnation of density functional perturbation theory, but for magnetic fields, and that's also implemented. So yes, you can do that. I'm sure there's also a roadmap entry on that one that I didn't cover, so it will also be in the roadmap. So NMR, yes. Optical absorption, also yes. So in the framework of TDDFT specifically, you can do that because we have TDDFT and even NFS dynamics now in the code. So linear optical absorption, yes. Especially for molecules and also periodic systems, it's a little bit more. I mean, I have first-hand experience now because we're trying to use in the group. I think I would say the molecular part very good, very well developed, no problems. Periodic part is a bit slow still. It's robust but slow, but certainly about to be more developed. It's an effort in the group of Yasuka Kanai in North Carolina. So yes, so it's possible. Try it out. Also in the roadmap, it's explained how to do it.
Is electronic absorption also possible with BSE?
No, not that I know of. Yes, not that I know of, unless you interface something with something else. I will rephrase my answer. If it's available, it's not very developed, or it's at a dev stage, because I know we have been thinking about this for a long time, but I have not seen other people other than me can say a better answer here, but it's certainly not in the roadmap. I think so.
Okay, and a second question from Aurélie. How does the code perform for metallic systems or systems with strongly correlated electrons?
So for metallic systems, the first question is metallic systems, right? Yes. Metallic systems very, very well. I mean, K-point handling is amazing. It's super parallelizable over K-points as well. So, no problems for metals yes. I mean, one thing that I don't know, I only talk about my own experience here in my group, together with my group, but, converging the electronic structure, for example, of metallic slabs and so on is quite great and robust in FHIMs in most cases. There are some pathological cases that will never converge, but in most cases, really, really good. It's different to some other codes that have a lot more difficulty converting things. For metals, really great. And then the other one was strongly correlated. Yes?
Yeah.
So there are there's a plus U implementation in the code that can handle more strongly correlated systems as well. You have to note that this is plus U in all electrons, which is different to most plus U's that you will find in other codes that are not all electron normally in the literature. So the values of the U I hear, I don't work with that directly, so I'm just saying what I know of broad knowledge are quite different that you have to use, but this is also covered in one of the roadmap contributions.
Thank you. I think we just have time for one more question, and we'll either answer the rest by typing, or you're invited to email us or Mariana if you have additional questions. So last question from Dimitri Ferha. Once the normal modes have been computed, how many additional calculations need to be done per normal mode to get the Raman spectra? Are these calculations more expensive compared to the numerical Hessian calculations?
Yes, maybe I just show here again quickly. Wait a second. So the overall answer to that question is yes. And I can tell you a bit more what you'll see in the tutorial tomorrow. So you have two ways to go about it if you like. Okay, so you can, for example, if you calculate the normal modes by finite differences here, right? You can, at the same time that you're calculating each one of the atomic displacements, you can also calculate, in this case, the dipole at each atomic displacement, or in this case, you can calculate the polarizability as well at each atomic displacement, okay? And if you calculate the dipole, for example, for non-periodic systems, this is not a huge overhead in the calculation. For the periodic system, it's a bit more of an overhead because you need to go through this Berry phase framework. So you have to calculate the Berry connection. This is done currently in reciprocal space, so it needs a little bit, for that part of the calculation, more K points and so on. So you'll see tomorrow, it's a bit more costly. Here, at the same time that you calculate the atomic displacement, you have to calculate also the polarizability tensors. And this is a bit more costly, maybe it's like doing 3 more GFT calculations per step or so. I don't know, a factor 3 or 4, because you have to calculate this response of the density, and this is done through the FPT, for example, in this case. So this also adds a bit of cost. It depends on your system how much it is actually. And then you can build this Hessian matrix and diagonalize it all together. So then you get the normal modes, and you also get the matrix of transformation, so you know the change in alpha in the direction of the normal mode directly. Another way to go about it is that to calculate all the normal modes without calculating either mu or alpha at that point of the calculation. And then with those normal modes that you have, you just displace back and forth along that normal mode, and you calculate the dipole there, and then you get the same element. You can choose the way you want to do it, but you always will have to calculate on top of your typical normal mode calculation either the dipole or the polarizability that you want. And here also through a trajectory, at each time step, you also have to calculate the dipole or the polarizability. And so that's a little bit extra cost. I mean, a little bit, or maybe even 3 times more, sometimes, something like that.
Okay, thanks, Mariana. So I think that will close the questions for this part. I'll just hand over back to Konstantin now before Alexandra's talk.
Thank you, James. Thank you, Mariana, again for the nice talk, as well as the Q&A session. Also, thank you to everyone who submitted questions. We tried to answer most of them via the chat box. Otherwise, feel free to write a mail or so also. We'll try to answer the mails then. The next talk is then by Alexander Tchenko. So thank you again for being here. We had a brief introduction in the beginning, so I think you can start right away, just sharing it, then dive right in.
Good. Do you see my screen?
Yep, that works.
Okay, fantastic. Thank you very much. So yeah, thanks, Konstantin, for the kind introduction. I'd like to also thank all the FHI AIMS team for, first for writing the code, but also organizing this webinar. And finally, I'd like to thank the audience for listening to my talk. So today I would like to talk a bit about solid electrolytes and how we can model them using FHI AIMS. As you all know, solid electrolytes are components of solid-state batteries. And of course, solid-state batteries are becoming of increasing importance in our technological world. And in particular, solid electrolytes are components that actually provide the source of lithium ions in solid-state batteries. Now, those materials are quite complex, so they're usually composed of a cationic framework, which is rather immobile, and anionic framework, which is immobile, and cationic lithium, part of the framework, which is actually mobile, right? Which is exactly the source of the lithium ions. And so there's a lot of puzzles, what I call ionic puzzles, in those materials that we need to solve in order to understand their properties and their functionality in real world. I'd like to start my talk in a very broad way by first telling you a bit about what I see is the main challenges in the field of atomistic modeling. So I'd like to start with this picture of what I call now the standard model of atomistic modeling, which relies on three fundamental pillars. Quantum mechanics, which is the main topic today. It gives us the ability with certain approximations to compute hopefully accurate forces that atoms feel in molecules and solids. Now, of course, that's not enough in order to understand the behavior of materials. We usually need to understand how things evolve under given conditions of temperature, pressure, and external environments. For that, we use statistical mechanics. And finally, machine learning is a fundamental third pillar that enables us not only to accelerate both quantum and statistical mechanics calculations, but also actually form statistical representations of how properties evolve in molecular and material spaces. But of course, all these pillars, really, I think the most fundamental pillar is that of quantum mechanics. Because if we make errors in our quantum mechanical force calculations, those errors will propagate often in an uncontrollable way into our statistical properties or into our machine learning potentials. So as we go about constructing more and more general or universal machine learning potential, it becomes especially very relevant to really have a very precise and accurate description of quantum mechanical forces. Now, usually we employ density functional theory to compute our approximation for quantum mechanical forces. And of course, DFT is in principle exact, but in practice, there is a price to pay, and we use density functional approximations or DFAs. So what DFT does is it achieves, in principle, a mapping from a many-body wave function, which is a 3n-dimensional object where n is the number of our quantum particles, to an effective three-dimensional electron density representation. Now, of course, there is a price to pay for this, in principle, very efficient mapping of what I would call a no-free lunch, because we end up having to approximate all the many-body exchange and correlation effects. And usually we do this by so-called semi-local or hybrid functionals, which are based on local and then increasingly non-local information in the electron density. So we start with the LDA approximation, we go to use the gradient and the GGA approximation, then we can use higher order derivatives of the density or the computing the exact exchange energy in hybrid functions. So this, of course, leads to well-known self-interaction errors that we usually alleviate by using hybrid functionals such as PBE0 or HSE. And then, of course, the second part which is missing is, so actually when we improve the exchange energy, we usually improve the electrostatics of our system. We also improve the description of Pauli repulsion. But of course, as you all know, semi-local functionals also miss the description of long-range correlations, and that, of course, subsumes the very important van der Waals interactions that Mariana already talked about quite a bit. So, of course, we also know in principle how to treat the long-range electron correlation in the context of density functional theory that requires us to go to so-called adiabatic connection fluctuation dissipation theorem approaches, which provide a non-local approximation to exchange and correlation energy. And here we kind of get some free lunch because we actually know what quantity we need to model. And this is so-called the density-density response function chi, which is a non-local function that measures the change of potential at point r prime, the change of the density at point r prime, to a change of the potential at point r. So, well, this function is, of course, a non-local and highly complicated function, time or frequency dependent as well. Nevertheless, if we could construct good approximations to this function, we could, in principle, get a very reliable way to include non-local electron correlations, van der Waals interactions, and so on. Now, usually we use so-called random phase approximation to construct this function, but that's also quite expensive for realistic materials. And so we end up doing something like this on the bottom of the slide. So instead of actually modeling the response function, we only model the van der Waals or the London dispersion part of it, right? And this can be done by multiple ways. For example, fragment-based approaches. This subsumes the Grimes, DFTD approaches, D2, D3, D4, the exchange dipole moment, XDM approach of Becker-Johnson, or the Tkachenko-Scheffler approach. The two-point density functionals, such as the VDWDF functional of Langers and Blomqvist, or the Vidrov-van Voorhis functional, are also doing something very similar. Essentially, although the formulas of these approaches look a bit different, but the physics underlying them is actually very similar. What you do is you define the polarizability of some local objects, and you compute the pairwise energy, the pairwise interaction between those objects. So some time ago, as Mariana also said, we've developed the MBD approach that essentially uses exactly the same formula as the exact adiabatic connection fluctuation dissipation theorem approach, but instead it's providing a model for the density-density response function using localized harmonic oscillators. Once you've parameterized those harmonic oscillators from the density using actually the Tkachenko-Scheffler approximation, you can couple them and solve the ACFDT equation to infinite order in perturbation theory. Once you do that, you get two-body effects, three-body effects, n-body and infinite order effects, actually, and that's the approach which we often use. Then in 2020, we went beyond this and we tried to actually make a broadly applicable functional for DFA plus van der Waals functional that actually can describe molecules, materials, and all classes of different materials on equal footing. We did this together with Jan Herman, who was a PhD and a postdoc in my group. And so essentially, the essential idea here is to get what I would call the best of both worlds. So we combine a two-point non-local functional of Vidrov-van Voorhis. We renormalize it to make it exact for the whole periodic table. And then we use this renormalized VV10 polarizabilities and employ this as an input to the MBD Hamiltonian. And then we solve the MBD Hamiltonian to get the many-body energy of, or the many-body long-range correlation energy of the system. So this really joins together two very general concepts in the field of van der Waals interactions, the non-local functionals and the MBD approach. And we've demonstrated that this actually works quite well for a wide range of molecules, materials, metals, ionic solids, and so on and so forth. And that's, of course, as Mariana said, implemented in the FHI AIM scope. Just to show how this works, so here on the left, I show you a performance of the MBDNL functional together with the PBE DFA for molecules, the S66 dataset on the left, and for 64 solids on the right, including metals, simple metals, transition metals, semiconductors, carbides, nitrides, and ionic crystals. And you can see that for molecules, it performs as well as the traditional molecular MBD at RSSES functional. This is very good performance. It's better than the VV functional. You see that in the VV functional, you get inconsistent accuracy as a function of separation distance between molecules. And also for solids, the performance is not far from the performance of the parent PBE function. Now, it's pretty hard to beat PBE. Actually, no one really beats PBE still, I would say, in terms of local, semi-local DFT functionals in terms of performance, its performance for solid state. In contrast, so PBE plus MBDNL works as well as PBE. In contrast, the original MBD functional fails for many of the solids because of so-called overpolarization problems. And so you cannot even carry out MBD calculations for many of the highly polarizing solids. Okay, so now let me go back a bit into the history as well to review what we understand actually about van der Waals interactions in hard solids. So it's not a surprise that van der Waals interactions, or dispersion interactions, are extremely important for molecular solids. For example, the benzene molecular crystal will not even assemble if you don't have the correct description of van der Waals interactions. But for hard solids, it turns out that we actually know very little about van der Waals interactions, even up to date. So here is our early work. I think this is really the first work together with my former student, Guoshu Zhang, who I hope is also hearing today. We asked the question of, can you really understand how important or not important van der Waals interactions are in ionic and semiconductor solids? And in this paper, we actually demonstrated that if you take PBE or HEC functionals and you add van der Waals dispersion interactions to it, all the properties, all the cohesive properties, lattice constant, cohesive energy, and bulk modulus actually improves. We only did this for 6 ionic and semiconductor solids, and then in 2018, we went ahead and actually did it for a large range of solids. In this case, this is the example of 23 semiconductor solids, where you can see that the inclusion of van der Waals interactions in HEC functional in particular actually gives you results that improve on the parent functional always for the lattice constant, the cohesive energy, and the bulk modulus at the same time. And actually, this gives you always results which are much better than the PBE sol functional, for example, which is still widely used to describe solid properties. And it's actually on the same level of accuracy as the scan functional, which is, of course, much more sophisticated and more expensive, and actually still needs to be corrected for van der Waals interaction. Of course, we are not the only people that worked on the importance of van der Waals interactions in solids. This is quite a prominent paper from Jire Klimesh and Angelos Michaelides, who demonstrated that by empirically optimizing semi-local exchange in dense functional approximations and coupling this to non-local van der Waals functional of Langres and Lundquist, can actually get better results than PBE for the cohesive energies of solids and get the lattice constant is essentially lattice constants of solids with actually the same accuracy as PBE. So this was quite a breakthrough, and of course this is a widely used functionals, for example, the OB88 van der Waals. Now going beyond solids, hard solids, to actually realistic solids, so solids with defects, which of course connects to the main topic of this talk, which is solid electrolytes. We also did early work with my former postdoc Van Gao at the Fritz Haber Institute, looking at what happens in terms of van der Waals interactions for defects in solids. So this is actually a work for silicon, right? This is simple silicon bulk, and silicon has 4 natural defects that are experimentally known. It has 3 different geometries for interstitials, so-called H, X, and T interstitials, and a vacancy. And in this work, we looked at how van der Waals interactions actually contribute to the properties, the stability, and the mobility of point defects in simple semiconductors. And we were extremely surprised because, semiconductors are, of course, tightly bound. They're chemically bound, and you usually do not consider van der Waals interactions to be very important. But we found in this work that for a particular migration between the H defect and X defect, the barrier actually is modified by 0.4 electron volts. It goes from 0.69 to 0.29 electron volts by including van der Waals interaction. And this modification of the barrier actually comes from 2 coupled effects. One is the modification of the geometry of your system in the presence of the defect. And the second one is that the transition state is actually the geometry of the transition state is also modified quite a bit. And so this is actually quite a surprise, and our results agree much better with the experiment and were later actually confirmed in explicit random phase approximation calculations by the Kressis group. Now, of course, these calculations are extremely expensive. They had to use very large unit cells actually here, but they basically confirmed our HEC plus van der Waals results with the RPA calculation. So this is just to tell you that the inclusion of van der Waals interactions stabilizes or sometimes destabilizes your system depending on the property that you are stuck. So this was the, let's say, old history. And now let me go to the main topic of my talk, which is the description of solid electrolytes. And in particular, once again, we will focus on the stability and the mobility of these complex materials. So this is work which we've done together with Swastika Banerjee, who was a postdoc in my group, and she's now assistant professor at IIT Roorkee in India. And the results of this work actually are about to be published in Nature Communications. So this paper is in the press. So in particular, first of all calculations that I've been presenting, I will be presenting are done within FHI aims using a variety of functionals, and I will comment on this later. So what we're interested in particular, we focus on the so-called argyrodite family of lithium supraionic conductors. These are so-called quaternary materials, so they have 4 components. You have, of course, lithium cations, you have halogens, you have sulfur anions, and then you have a semi-metal. It can be phosphorus, silicon, or germanium. And so, as you can imagine, this combination of 4 components, 4 elements, can give rise to a large chemical space and a large wide set of properties of these materials in terms of both the stability and the mobility of lithium ions through these materials. These materials often alternate between ordered structures and disordered structures, so they can be disordered between the halogens and the sulfur atoms, and this again just makes the chemical space even more complicated. And so we would like to understand this chemical space, and in particular, we would like to understand what level of theory is required to actually accurately model the stability and mobility of these materials. So as I said, the materials are characterized by having essentially an almost immobile anionic framework, right? And then the lithium is diffusing through the material, so that's the mobile part. And so you need to kind of be on this verge of stability and instability in order to enable high enough mobility of lithium ions. And so we will focus in particular on 4 different types of argyrodites. So you have chlorine-based, iodine-based, mixed anion, and mixed cation. These materials have been experimentally characterized, and the ion mobility has been actually measured. So as you can see here on the sigma RT, this is the room temperature ion mobility, or ion conductivity, let's say. You can see that it can vary by 4 orders of magnitude, depending on the particular structure of the material. So it varies, between 10 to the minus 3 to 24. And in particular, it's not known why. So for example, if you look at the chlorine-based or iodine-based material, the iodine-based one has a very low mobility. But people were actually expecting that the inverse would happen because iodine is a highly polarizable ion compared to chlorine. And so people were expecting that higher polarizability should actually correlate to higher mobility. But instead, something different happens, right? Something contrary happens. And so this remains unexplained. If you look at the right-hand side, this is the average barriers that have been experimentally measured for ion mobility. And you see that actually they are all, they don't change too much depending on the material, which means that the prefactor, which essentially measures how many different pathways for diffusion exist in this material, right, are there. So you need to understand both the prefactor, all the different pathways for lithium mobility, and also the barriers. So let's first look, in order to understand the mobility, we first need to understand the stability, the general stability of the material. Let us start by looking just at the global structure of these materials by measuring the cell void. So we look now at just 2 of these materials, the chlorine-based and the iodine-based. So the experimental volumes are in blue and green here on the left. And so you can see that semi-local functionals, PBE or HSE, actually give pretty bad results. If you include van der Waals interactions, for example, using the Tkachenko-Scheffler approach, you overstabilize those frameworks, although the difference in volume between the two materials seems to be actually accurately captured. PBE plus D3 seems to work well, but actually if you move to HSE plus D3, which is just a change of the functional, the results are much worse. And this is actually surprising. We don't understand why there's such sensitivity to change in the parent functional that actually does not happen with the Tkachenko-Scheffler approach, which gives exactly the same results from PBE to HSE. On the other hand, the PBE Sol functional, the OP-B88 functional, actually are not giving too bad results, although sometimes they underpredict the difference in volume between the two different structures. Now let's look at the right, at the HSE plus MBDNL functional, which to me is really the only approach that includes the non-locality in both the exchange and in the correlation. And if you do that, you see that the results are getting actually pretty close to experiment, in particular if you go from 0K structure to 300K structure by including vibrational unharmonicity and 0-point energy correction. And you see we get results which are pretty close to experiment. Now, of course, getting the global structure right is not the only thing you need, but you also need to focus on the local structure within the unit cell. So the rGyrrodite materials have very specific constraints because of their structure. For example, they usually have very symmetric chlorine-lithium bonds, and also this tetrahedra of the semi-metal with the sulfur. And so what we've done is that we've taken all possible rGyrrodite structures from the CSD data set, right, of crystal structures, and we've done just an average of those structures. And we've constructed, for example, here the GOVAR distribution of chlorine-lithium distances. And this is shown in black in this plot. One thing you immediately see is that at 3.5 angstrom, some functionals such as PBE Sol and OPT-PBE, OPT-B88, sorry, they lead to a peak which is absent from experiment. And this peak arises from an inhomogeneous distortion of lithium ions around a chlorine ion. And that's actually wrong, right? That shouldn't exist. That's not there in experiment. On the other hand, this symmetry is not present when you go to the highest level of theory, HSE plus MBDNL, and you get the correct homogeneous description of the bonding between chlorine and lithium. Okay. Overall, HSE plus MBDNL has a really, really good description here compared to experiment. We cannot compare one-to-one because we are doing a simple average over structures. But as you can see here, in particular, if you take the disordered structures in our calculations, we describe all the prominent peaks really. Okay, so now we've assessed the stability and we've demonstrated that HSE plus MBDNL gives you both accurate global geometries and also local geometries in the unit cell. Now let's move to the lithium diffusion. So Swastika in her previous work have actually done ab initio molecular dynamics calculations for two different rGyrrodite materials, and she looked at how diffusion pathways vary from one material to the other. And what she has found in particular is that in this chlorine rGyrrodite, you have cage-like lithium diffusion. You see here these concentrated cages, while in mixed anionic material, which has the largest lithium conduction, you actually form this interconnected domains that form diffusion channels, and that explains why the lithium conductivity is so high in this mixed anionic materials. So there is a wide range of possible lithium jumps between the different parts of the framework. So in order to study this, we first focus on the shortest diffusion path for lithium diffusion in these two different materials. Again, the chlorine-containing material on the left and the iodine-containing material on the right. And let's look at the barriers here. So here is the on the x-axis you have the diffusion path, on the y-axis you have the relative energy. And what you see is that depending on the functional, the pathway, the barrier is actually quite different. So in particular, if you include van der Waals interactions using the Tkachenko-Scheffler approach with the pairwise approach, you see that the barrier is getting, the transition state is actually getting overstabilized. So the van der Waals energy is much higher in the transition state. This is this red dashed curve here, or the pink dashed curve. And for that reason, the barrier is actually very low. With the many-body MBDNL approach, the van der Waals energy is essentially homogeneous over the whole transition path. So it doesn't change. So there's a complete flat van der Waals energy, and that's why the barrier is actually much higher and also agrees much better with what the experiment actually sees. Although we cannot compare 1-to-1, but that's what we would expect. We'd expect the higher barrier here, a bit lower barrier for fluorine, and that's actually consistent. One way to assess why this change in the barriers happens between pairwise description of van der Waals interactions and the many-body description is looking at the geometry of the framework in the minimum and in the transition state, right? So here the two columns are the minimum distances between lithium and sulfur atoms and lithium and halogen atoms. And on the right, the right two columns are actually the distances for the transition state. And as you can see in this pairwise dispersion, the in the minimum configuration, in the equilibrium configuration, the difference in geometry between pairwise dispersion and many-body dispersion actually is very, very small. But when you move to the transition state geometries, you realize that there can be very drastic changes, especially for the mixed anion framework here. For example, the lithium chlorine distance actually changes from 3.47 to 2.81. It's a huge change in the geometry, which kind of agrees with our old work on diffusion of silicon, on defects in silicon, where we also observed quite significant differences in the geometry upon including van der Waals interaction. We see the same here. So basically, softer frameworks, which is exactly happens here for this mixed anionic framework, they can lead to very high changes in the distance due to the inclusion of many-body dispersion. That's quite surprising, but that actually explains why there's such large differences in the transition path.
3 minutes, please. Oh, yeah, almost done.
Yep, this brings me to my conclusion. So I have described a range of comprehensive calculations that we have done to understand different properties of solid electrolytes, in particular the argyrodite family. We found that the impact of non-local interactions, both in the exchange by using HSE functional and in the long-range correlation by using the MBDNL approach, actually has high impact on both the stability of these frameworks and the mobility of lithium ions through the framework. We saw that the really important thing to get right is the local structure of these materials, not just the global unit cell, which is what most people focus on, and in particular, the local structure of the structuring of sulfur and lithium ions actually can change quite a lot in the pairwise treatment of dispersion interactions versus MBDNL treatment of dispersion interactions. Once again, this work will be published soon in Nature Communications. And with that, I'd like to thank you for your attention.
Thank you very much, Alexander, for your great talk. Thank you for staying on time. Of course, now we again come to the Q&A session. As before, feel free to ask in all of our different channels, whether YouTube, Kushare, or here in Zoom, and then we'll try to answer your question as much as possible. So I hand over again to James to manage the Q&A. Thank you again.
Thank you. Konstantin, and thanks, Alexander, for the nice talk. And I don't see any questions in the Q&A right now, so I'll just give a moment for people to type any. Or again, if you want to speak your question, then just raise your hand. But maybe I could just start with a quick question. So in the chlorine lithium distances G of R plot you showed, why was the two peaks at the low distances at the experiments and just one peak for the theory?
Right. Yeah. So here one thing you can already see is that the level of disorder, right, matters a lot because, for example, if we move from the from this blue solid line to the blue dashed line, which is HSE plus NBDNL for an ordered structure and for a range of disordered structures, you already see quite some difference there, right? And the peak actually moves much closer to the experiment. There's some incipient change in the gradient of the dashed line if you look very closely here, although there's several overlapping lines, but we don't really get a peak, right? We just took I actually don't remember how many disordered structures we calculated, but we didn't really took all the disordered structures from the experiment, right? So it might be that we just subsampled the structures where this particular second peak appears.
Okay. Still nothing in the one in the paired in the Q&A. So maybe this. So this is from Ramsevak Kashyap. So is dispersion also affecting paddle wheel effect, or are there vibrations? In my opinion, this can also affect the lithium migration.
Yeah, that's right. So in the paper, we actually look very carefully as well at the phonons of these different frameworks, and we do find that the dispersion, the treatment of dispersion interactions, has a very strong effect in the low frequency phonons that actually dictate the lithium migration through the framework. So yes, so actually the phonon modes change qualitatively depending on which treatment of dispersion interactions you have, and we have some arguments in the paper why actually the NBDNL phonons agree better with what is experimentally observed in the systems. But this is something where actually I think the next step would be to try to train machine learning potentials on this data and actually simulate dynamics and observe the actual lithium migration. And this would be, you know, the next thing to do in this system.
Thank you. So question from Sandeep Kumar. So what are the best strategies for minimizing disorder in LMSX to achieve an optimized structure?
So the disorder is actually a natural phenomenon that happens in these materials, and in fact, because the highest mobility is observed in these mixed anion materials, right? Disorder is something that actually helps, right? The disorder is specifically between the halogens and sulfur. Actually, what helps to maximize the mobility. But of course, you want to have certain mobility, but you also want to have a certain stability, right? So you always optimizing for mobility and stability at the same time. And in fact, these mixed anions are also, I think they decompose electrochemically. So unfortunately, you know, in order to optimize both properties, we don't have the answers yet how to do this. I think this would be the next thing to do, again, by explicit molecular dynamics simulation.
Thank you. And the question from Sandy, can ab initio molecular dynamics be done at the HSE 06 level in FHI aims in a practical computational time for solid electrolytes or cathodes with transition metals?
So is the question whether we can carry out explicit ab initio MD?
Yeah, I guess carry out explicit ab initio MD with HSE 06 and in a reasonable time or reasonable.
Okay, yeah. So what I would do is I would actually I would just construct a machine learning force field using the HSE plus NBDNL as forces as an input, right? I think that's what I would recommend, right? I think that the speed, as Mariana has discussed in her talk, the speed of HSE plus NBDNL calculations actually is sufficient to generate enough reference data to construct machinery and force fields here for these materials. I think you probably need just a few thousand calculations for a few thousand structures, which would allow you to construct, a general machinery and force fields for this class of materials. We haven't done it, so it might be more complex than that. But I wouldn't actually recommend running explicit ab initio MD on the systems because I think that the machinery and force fields, that's the way to go now.
Can I just add, you can check the timings in that publication that we gave. You can see for your system size, more or less, what would be the cost. And if you have a really large computer, maybe the computational time won't be won't take many years, but the computational cost will be insane, okay? So doing explicit ab initio MD on these large disordered materials, I think, is not really the way to go in general. I agree with Alex completely. So yes, so a machine learning potential, but then the nice thing is that you can do large structures that capture all of this disorder in the training set, because you can calculate quite a few points and that's it. But MD, you need hundreds of thousands or even millions of evaluations, right? So it's another game.
Thank you for the answer to this. So I don't see any open questions anymore. So maybe I can hand back over to Konstantin now to close the session.
Thank you, James. Thank you, everyone, for your questions. Of course, thank you to our two speakers, Mariano Rossi as well as Alexander Tchachenko, for two great talks. I hope you all enjoyed them today. I just want to remind you all of the tutorials tomorrow. So, as I mentioned, we will have two sessions, one in Berlin morning time as well as one later in the afternoon. So even if you want to join now and ask more questions, feel free to do so. It's open to everyone. The links will be the same. And as mentioned, if you signed up for the online tutorials and wanted to have access to these resources, you should have already gotten a mail from us. Otherwise, I want to thank you all again for joining us today. And I hope you enjoyed this session or this iteration of the webinar. We have, of course, new ones coming up. So as always, check our socials and our website to be reminded whenever we have a new webinar scheduled. So thank you again to everyone. Thank you again to our speakers as well as the full audience. And I hope you all enjoyed. Thank you.
Thank you.
Right. Bye-bye.
Bye-bye.
Record.